Hi, in this video we continue solving exercise sheet 3 and we take exercise number 7. We have f of x is equal to x minus e of x, g of x is equal to the absolute value of x minus 1, and we take the function h equal g round f, and we need to study the continuity of h over minus 1, 1. So h of x being equal to g round f of x, it's equal to the absolute value of x minus e of x, right, minus 1. Then if x belongs to minus 1, 0, in this first case, we have e of x is equal to minus 1. Of course, we need to study also the case when x is between 0 and minus 1, and then we need to study the points 1, minus 1, and 0. Okay, so in this first case, if x is between minus 1 and 0, e of x is equal to minus 1. Then h of x will be equal to the absolute value of x, which is equal to minus x because x is negative, and minus x is a continuous function. Then h is continuous in this case when x is between minus 1 and 0. Now take the case if x is between 0 and 1, then e of x is equal to 0. In this case, h of x will be equal to the absolute value of x minus 1, which is 1 minus x, since x is between 0 and minus 1. So it's the positive version, it's 1 minus x, which is continuous. Then h is continuous in this interval. Now we need to study the points 1, 0, and minus 1. Well, h of minus 1 is equal to g round f of minus 1, which is equal to 1. h of 0 is equal to 1. h of 1 is equal to 1 as well. So the limit when x tends to minus 1 plus of h of x is equal to the limit when x tends to minus 1 plus of absolute value of x, because this is the version of h of x when x is on the right of minus 1. So this is equal to 1, and it's equal to h of minus 1. Then h is continuous at the right of x equal 1. Also, limit when x tends to 1 minus of h of x is the limit when x tends to 1 minus of x minus 1. This is the expression of h of x on the left of 1, which is equal to 0, and it's different than h of 1, which is equal to 1. Then h is not continuous at the left of x equal 1. And finally, limit when x tends to 0 plus and 0 minus, so 0 minus first of h of x, is equal to the limit when x tends to 0 minus of absolute value of x, because this is the expression of h at the left of 0, which is equal to 0 and not equal to h of 0, while the limit when x tends to 0 plus of h of x is the limit when x tends to 0 plus of absolute value of x minus 1, then it's equal to 1, which is equal to h of 0. Then h is not continuous at the left of 0 and is continuous at the right of 0. In exercise 8, we have a function f of x equal to x over 1 plus absolute value of x, and we need to prove that f defines a bijection on -1, 1. So first we need to understand what is the function f. That's why, since we have an absolute value, we'll take two cases. If x is positive, then f of x is equal to x over 1 plus x. Then the derivative will be f prime of x equals to 1 plus x minus x over 1 plus x squared, which is equal to 1 over 1 plus x squared, and it's positive. And if x is negative, then f of x is equal to x over 1 minus x, which means that f prime of x is equal to 1 minus x plus x over 1 minus x squared, which is equal to 1 over 1 minus x squared, and which is also positive. Then f is strictly increasing on R, of course on the domain, which in this case is R. Then f has or is continuous, strictly increasing from the domain, which is R, into what? Into the image, and we need to find the image. So to know it goes into what, since the function is increasing, so we need to calculate the limit when x tends to plus infinity, which is the boundaries of R of f of x. So when x tends to plus infinity, it's equal to 1, and the limit when x tends to minus infinity of f of x is equal to x over x 1 minus x, so it's minus 1. So into, it goes from R into minus 1 1, so it's continuous, strictly increasing from R into minus 1 1. Then it defines a bijection from R into minus 1 1, and it has an inverse function f minus 1, continuous, strictly increasing from minus 1 1 into R. So it goes in the other way around. So f minus 1 is defined from minus 1 1 into R, and we need to find now the expression of f minus 1. So we take y is equal to x over 1 plus absolute value of x. So if x is positive, then y is equal to x over 1 plus x, which means that y plus yx is equal to x, then x is equal to y over 1 minus y. And if x is negative, then y is equal to x over 1 minus x, then x times 1 plus y equals to y, which means that x is equal to y over 1 plus y. Then combining both, x will be equal to y over 1 minus absolute value of y. This is the expression that combines both. Therefore, f minus 1 of x will be defined as the function x over 1 minus absolute value of x. So this is the expression of f minus 1. In number 9, we have a function f that is going from the segment AB into the segment AB, the same segment, and continuous. And we need to prove that there exists x0 such that f of x0 is equal to x0. This kind of points, where the image is the point itself, they are called fixed points. So this is a fixed point in AB. If you want to imagine it, imagine that you have a function that is going from 0 1 into 0 1. so 0, 1 into 0, 1, and that is continuous. Can you find such a function continuous such that it doesn't intersect y equal x? So this is y equal x. If you start your function like in here, so the image of 0 is in here, and you do your function, if you will, you need to define an image for all the points between a and b, so between 0 and 1. You are obliged, whether by ending your function at the point b, so we'll have a point b such that f of b is equal to b, or to end your function somewhere in here, so you'll have a point here such that f of x is equal to x. So for sure you are obliged to have a point satisfying f of x is equal to x. So to write this properly, we say let g of x be the function defined by f of x minus x. Now g of a is equal to f of a minus a. G of b is equal to f of b minus b. Well, g of a that is equal to f of a minus a is of course positive, because this is equal to f of a minus a, and f of a belongs to ab because it's an image of the function f. So since it belongs to ab, then it's greater than a, so then it's positive. And f of b as well belongs to ab, then it's less than b, so this is negative. So we constructed a function g such that g of a is positive, g of a is negative, but they can be equal to 0. So first, if f of a is equal to a, so g of a is equal to 0, then problem solved, then x0 is equal to a. If f of b is equal to b, then also problem solved, because x0 that I'm looking for is equal to b. If f of a is not equal to a and f of b is not equal to b, then g of a is strictly positive and g of b is strictly negative. And since g is continuous, then it's a continuous function taking positive values at a and a negative value at b, then the intermediate values theorem allows me to say that allows us to say that there exists x0 that belongs to ab such that g of x0 is equal to 0, since g is taking a negative value and a positive value. And since g of x0 is equal to 0, it means that f of x0 minus x0 equals to 0, then x0 is equal to f of x0, and we found the point we're looking for.